Hello everyone, welcome back to Curiotech. My name is Suchi and we are moving forward with the series of DS. The next topic is asymptotic notations, which is an important concept of design analysis of algorithm or DSA. So whenever we design an algorithm, we want to know how efficient it is. But efficiency can be measured in different ways. That much we have already discussed. For example, one algorithm may take 10 seconds for an input size of 100, while another may take 2 seconds. But is the second algorithm always better? Necessarily not. What really matters is how the running time grows when the input size becomes very large. So what we are basically interested in is growth. We check according to the input size how the growth performs. Alright, how that algorithm performs when the input size become very large. So why do we need asymptotic notations is we focus on growth, not the machine dependent running time. We study how the algorithm running time grows as the input size n becomes very large, and also we ignore the constant and lower order terms when comparing growth. The result is a compact description of algorithm and efficiency. Suppose this example, here there are three terms, that is 3n square, 5n and 7, right? That means n square is greater than n and n is greater than 7. That means n square dominates here. So we can directly say that the complexity is big O of n square. We always represent the complex asymptotic analysis by representing it with the highest order term, and that would be big O of n square. We have already discussed a little bit of it in the previous video, so I am explaining it in detail here. There are multiple notations that we need to keep in mind. So first one is big O notation, second one is theta notation, and third one is omega notation. All of them has a different categories. That would be worst, best, and average case. Now whenever I have studied this concept, there was one example that has always stayed with me, and let me explain that example for you. Suppose you want to build a house. And you went to the contractor after finalizing the design and everything. You went to the contractor and told him that this is the design I want to get for my house, and I want you to build it. So this much is my budget, and you tell me how much will it take from your end. So suppose your budget is 45 lakh, alright, and you told to the contractor that my budget is this much, and you tell me how much will it take according to you. So he calculated and he told you that minimum it would take 40 lakhs, right? Minimum it would take 40 lakhs. So if he is saying that minimum it would take this much and it is already under your budget, right? So that would be the best case, isn't it? That it is already under your budget and it is giving you he is giving you the complete house under 40 lakhs. So that is your best case, right? Next, it says that according to the span of the construction, right, it may take 1 year or 1.5 years. So according to that part, the labor cost may get higher, and also the construction cost may get higher, the material cost can get higher. So at most it would take 50 lakhs. Right? So this would be your worst case, because it is going over your budget, and also it is going over budget, and also you do not have it under budget, right? Not nearly up to your budget also, right? It is over your budget. So it is your worst case. Average case would be if it is according to your budget. So there are three cases. So when I am talking about worst case, that is big O of n. We are talking about the best case, that means omega of n, and when we are talking about average case, that is theta of n. Alright, so these are the three cases that you need to keep in mind. So first one is big O notation. What does it mean by big O notation is, it is asymptotically upper bound. Upper bound means it gives you a bound where the actual growth will not cross that bound, Big O tells us that beyond some point, Fn does not grow faster than the constant multiple of Gn. Now, what is this Fn and Gn? This Fn here represents the actual growth, and the Cgn or Gn represents the referential growth. Alright. Now, in this example here, 3n square plus 5n plus 7 equals to big O n square. Why? Because n square is dominating and we are saying that the complexity would be big O of n square. Now, let's take this example and let me clear you the graph. So, here Fn is the actual growth, Cgn is the referential growth. This tells you that this Fn is greater than n and less than equals to Cgn. Alright, that means this Fn will not go beyond this Cgn. This algorithm will not go faster than the asymptotic bound that we have already given. Imagine if I tell you that a student will never score more than 100 marks. I am giving you the upper limit here. So, that is the big O notation when you get the upper limit. Alright. Next is omega notation. Omega notation is the lower bound. It tells you the lower bound. That means omega tells us that beyond some point this Fn, which is the actual growth, grows at least as fast as the constant multiple of Gn. Right? This means that it is giving you a lower bound. That means up to from that point, that is the Cgn, beyond this Cgn this function will not go. Right? That means but it wants to say that Cgn is less than equals to Fn. Cgn is less than equals to Fn. So, if I give you an example in it, that means I would say, suppose I tell you that a movie will take at least 2 hours. That means that is a lower bound. It may take 2 hours, it may take 2.5 hours, it may take 3 hours, but it won't be less than the given bound. So, means Fn grows at least as fast as Gn asymptotically. Alright. So, here in this example we say that it takes omega of n square, because the n square term guarantees that the function grows at least quadratically. Alright. Next is theta notation. So, this notation is the average bound or the tight asymptotic bound. Theta gives us both an upper bound and a lower bound. It describes the exact asymptotic growth rate up to constant factors. Now, see here, there are two referential growths, and in between that referential growth there is your actual growth. So, if we want to compare it, that means the C1Gn is less than equals to Fn and Fn is less than equals to C2Gn. So, let me write it down. C1Gn is less than equals to Fn and Fn is less than equals to C2Gn. So, that is the tight bound, means an average case. Alright. So, here if big O gives us the ceiling and the omega gives us the floor, theta gives us the both ceiling and floor value. You can think of it like that. Next are the little o notation and little omega notation. these are called not asymptotically tight notations. By not being asymptotically tight means they are not exactly correct, means they are not exactly they do not exactly give us the approximate value, or you can say that they grow strictly slower than the referential growth. Strictly slower, that means they don't go up to that referential growth. Either it is less than or it is greater than. Either it is less than or it is greater than. It is never equals to that referential growth. Alright. So here it is an upper bound that is not asymptotically tight. That is not asymptotically tight. It tells us that the function grows slower than the other value. Alright, that means it grows than the referential growth. It grows slower than the referential growth. So little o strictly is a smaller growth. The ratio idea would be Fn upon Gn tends to 0. Next is little omega. Little omega notation is also a not asymptotically tight notation. So but it gives you a lower bound that is not asymptotically tight, and the little o would give us the upper bound that is not asymptotically tight. That means here is also it follows the strictly larger growth. It should be either greater or it should be either smaller, not equals to. It won't reach the referential growth. So Fn equals to omega Gn means that Fn grows strictly faster than the Gn. Alright. Now here it is about the all notations at a glance. These are the all notations that we talk about: big O Gn, big omega, theta, little o and little omega. These are the meanings of it. If we are talking about big O, that means upper bound. If we are talking about omega, that means we are talking about lower bound. And if we are talking about theta, that means we are talking about an average bound which would give you the upper plus lower bound. Big O Gn, it would be strictly upper, and when we are talking about omega Gn, that means it is strictly lower. Alright, and these are all the bound where we discussed, and by through this slide you can directly see and remember all the concepts of it. These are the growth rates, and you can see log n would be the least one, then n log n, then n square, n cube, 2n, n factorial and so on. Alright, these are the typical, or this is the typical order of growth rate, and you can also say a comparison of the growth rate functions. This is the recap of the whole session we went through. So we went for the upper bound, lower bound, tight bound, strict upper and strict slower. These are the 5 symbols that you should remember. Big O, upper bound is always represented by big O, and lower bound is always represented by omega, and this represented by theta, and this is little o and this is little omega. Alright. So whenever you see an algorithm, don't just ask how long it takes for one particular point. Ask how its running time grows as the input size become very large. That's exactly what asymptotic notation helps us understand. So if you found this explanation useful, subscribe to CurioTech and for more concepts from data structure and design analysis of algorithms.